went in the construction of this famous integral. And actually, there was a very nice expository paper by Dror where he produced some deep connection between Lie algebra representations and weight systems. And actually, later on, I read a paper by Dror when he gave a very nice expository a very nice exposition about one homology, and actually Dror did quite a lot in knot theory and described a lot concerning many aspects of the most important parts of the knot theory. And today he is going to convince us that he still doesn't understand the Alexander polynomial, and I hope by the end of the talk you will believe it. So Dror, please start your talk.
Okay. I understand the Alexander polynomial better and better and better, but I still don't. Okay? So, first of all, here's the lecture room. You've never been to my lecture room, so you should see where I'm standing. And more about technicalities. So, I actually use, the main reason I give talks is to self-motivate to learn more. So I set a goal that I haven't achieved yet, and then I struggle to reach it in time. And today it ended up making the abstract irrelevant, because I actually made progress as I was preparing for this talk. So I'm still uncomfortable with the Alexander polynomial, but in different ways than before. So here is one place where I'm still uncomfortable. I'll mention more later. So I can compute the multivariable Alexander polynomial. So there is something, an invariant of knots, which will actually be defined in a sense later in this talk, or invariant of links, which assigns a polynomial to every link. And here is the polynomial associated with sorry, what was that? I'm sorry. Here is the polynomial. Sorry, I'm having technical difficulties. Here is the polynomial associated with the Borromean links. So I can compute this polynomial really fast. But the multivariable Alexander polynomial also satisfies so-called skein relations. Skein relations are relations like here. So if you have a link, and within it you can find a chunk that looks like the chunk on the left here, then you can replace it by the second chunk, or by the third, or by the fourth. So you will get 4 different links. And the claim is that the multivariable Alexander polynomial of the first 2, when you sum them, gives the sum of the invariants of the last 2. This is the equation written schematically down below here. So I can prove such relations completely systematically, but only slowly. So I'm a bit uncomfortable about it. You'll see what I mean a bit later. Okay. And I should say that the talk, to a large extent, is an elucidation of the PhD thesis of 2 of my former students, Jana Archibald and Eva Halacheva. And I also want to thank Roland van der Veen for comments. And I should mention a technicality. I got a notice that there is supposed to be a fire alarm testing today in my building. So if this happens, don't panic. It's only a test, and anyway, only I will burn. Okay. Suppose I wanted to prove skein relations. So relations such as the relation down at the bottom here. Let me tell you what would be heavens for proving such relations. And actually, to be honest, I'm talking about virtual knot theory here, so skein relation for virtual knot theory. If you don't know what it is, it's mostly irrelevant. So mostly whenever I say virtual knot, just think of an ordinary knot. But what I'm speaking about is more properly about virtual knots. It's more exact when we talk about virtual knots. So I have to make a definition, and first I'll make it completely formally, and then you will see how it's related to knot theory and why it's valuable. So a contraction algebra is a big object. It's an assignment which assigns a set, let's call it T, of calligraphic x and x to any pair of finite set calligraphic x whose elements will be denoted by Greek letters, and uppercase x whose elements will be denoted by Latin letters, provided these two finite sets have the same cardinality. So it's a big assignment of sets to finite sets. And it has several operations. So there is a disjoint union operation. So there is an operation going from T of calligraphic x and x cross T of calligraphic y and y into T of the unions, provided the sets are mutually disjoint. So calligraphic x is disjoint from calligraphic y, and x is disjoint from y. There is a second set of operations. So if you have a lowercase x in uppercase x, and if you have a Greek psi in calligraphic x, then there is a contraction operation cx psi going from t psi x into, well, one thing that the contraction operation does is to remove one element from the target set. So it removes Greek psi from calligraphic x and Latin x from uppercase x. And then there are renaming operations, which I will not really mention or will not really discuss in detail, but all they do is they rename the labels. So basically, I could have said it in a more functorial language, but I don't want to bother. So basically, if you have a map from x to y and from calligraphic x to calligraphic y, you have a corresponding map from t of xy to from t of xx to t of yy. Okay? And then, of course, you don't just have operations, you also have axioms, and I will specify the axioms after the examples. I think it will be clearer that way. And I should say that if you have a ring, then you can say that a contraction algebra is R-linear if these spaces are not just sets, but in fact, well, vector spaces, or more precisely, modules over that ring. And then all the operations are, the binary operations is bilinear, and the unary operations should be linear. Also, you can add some unit properties, and I will not bother to do that. And if you add the unit properties, then what you get is called a willed prop. But again, I don't want to go there, the language is different. Okay, so examples. Here is the example that motivates the subject. Okay? So let T of calligraphic x and x be the set of virtual tangles. Again, if you don't know what virtual means, forget it. Just ignore, just say to yourself tangles. With incoming ends, with ends labeled by the calligraphic x, and with outgoing ends labeled by uppercase x. So for example, here is a tangle. So a tangle is a piece of a knot drawn in a piece of the plane. So here is an example. And the incoming strands are labeled by Greek letters, Xi1, Xi2, Xi3, and Xi4, and the outgoing strands are labeled by Latin letters. So that's an example of an element. In fact, this particular one is an element of T of 4 Greek letters, Xi goes from 1 to 4, and 4 Latin letters, Xi, I goes from 1 to 4. Okay? Now, the disjoint union operations are the disjoint union operations. So if you have two tangles, T1 drawn in one piece of a plane, and T2 drawn in a second piece of the plane, then their disjoint union is the operation of drawing them side by side in the same plane. It's almost do nothing. Okay? The renaming operations are, so you know, basically I can rename the label, so the end. So instead of calling this X1, I could call it George if I wanted. Okay, so there are renaming operations. And the interesting operation, the truly interesting operation, is the contraction operation. So Cx psi is the operation of connecting the head x with the tail psi. So for example, Cx4 psi2 would look at x4 and at psi2 and add an additional connection between them without introducing any new crossings. So if you know virtual tangles, you know what it means. If you don't know virtual tangles, then my definition is a little bit wrong because you will have to insist that the contractions will occur only between neighboring things, because only then it makes sense to connect without possibly crossing other things, okay? But again, ignore this technicality. Okay, tangles can be made linear by allowing formal linear combinations. And second note is that tangles is finitely presented. So why is it finitely presented? Basically, it is generated, you know what, let me see if I can, sorry, where's the mouse? Here. Let me see if I can add a page, append page, I'm sorry, that will take a second. And good. So why is it finitely presented? It is finitely presented because it is generated by the undercrossing and the overcrossing. Of course it is generated by these two because basically you can write any tangle by taking these two, taking the disjoint union of several copies of these two, and then applying contraction operations. So you contract this with this, contract this with this, contract that with that, and of course you can get any tangle you want by doing these contractions. And then it is subject to relations, and the relations are the usual relations of knot theory. So the Reidemeister 2 move, the Reidemeister 3 move, this is equal to, what is it equal to? This, and the various Reidemeister 1 moves. So this is Reidemeister 3.
So you drew, you drew the same, not Reidemeister 3 by identity.
Okay, so I blundered, but I mean, okay, this is Reidemeister 3, thank you. And then there is Reidemeister 1, which says that you can undo kinks. All of these relations are relations between the generators. This, the left-hand side of Reidemeister 3 says that if you take 3 generators and contract them in a certain way, you get the same 3 generators contracted in a different way. So that's a relation. Okay? So, so as I mentioned, sorry, what's happening now? It's refusing to scroll. Yeah, so as I mentioned, this category of this contraction algebra of tangles is finitely presented. Okay. Oh, this should be node 3. So I should say that if you have a morphism of contraction algebras, well, it's clear what a morphism is. It should map the sets of one contraction algebra to the sets of the other while intertwining the operations. So if you have a morphism of contraction algebras from the contraction algebra of tangles into some algebraically defined contraction algebra, something made out of matrices, exterior algebras, tensor powers of vector spaces, I don't know, something. Then you get an invariant of virtual tangles, which is in particular an invariant of knots and links. And furthermore, it would be an ideal tool to prove skein relations. So if you wanted to prove this skein relation, all you would have to do is to compute the value of the invariant of this, the invariant of this, the invariant of this, the invariant of this. If your target space is a linear contraction algebra, you will verify this identity in the target space. And if it holds for every possible completion of this. Because it will hold if you compose it with anything else. So you've proven a skein relation. So basically, having morphisms of contraction algebras is a good thing. Okay, now I need to give you more examples. So here is an example I will not use, but you should be aware of. So if you have a finite dimensional vector space V, you can define V calligraphic X and then Latin X, sorry, that's a typo, to be the calligraphic X tensor power of V dual tensor the X tensor power of X, and then of V, sorry. And then disjoint union is just tensor operations, is just tensor product. Renaming is just renaming the factors, and the operation of contraction. So you see an element of V of this contraction algebra would look like a tensor in V dual, tensor V dual, a certain number of copies of V dual indexed by the calligraphic X, tensor a certain number of copies of V, tensored, labeled by the uppercase X, and then Cx psi will be the contraction of a tensor factor here with a tensor factor here. And it lowers the number of factors just as you would expect. Okay? Good. So now I can go to state the axioms of a contraction algebra. They're really, really simple. Basically, contractions commute. So, you know, if you have a tangle or some other contraction algebra, then contracting here commutes with contracting here. So Cx psi followed by, this is notation for followed by, this is composition going from left to right. So Cx psi composed with Cy eta is the same as Cy eta followed by Cx psi. This is the interesting axiom. Then there are silly axioms. So the disjoint union is commutative and associative, and it commutes with contraction. So if you take the disjoint union of two things and then contract, it's the same as first contracting and then taking the disjoint union. And everything behaves well with respect to renaming. So renaming and then contracting is the same as contracting, and then well, then you don't need to rename. The things you contracted are gone. So anyway, the axioms are easy. The only interesting axiom is that contractions commute. Okay. Questions, comments so far? So far I'm just setting up some algebraic context. Good. Yeah?
Just a quick question. With the contraction, are we trying to get rid of the calligraphic X elements in the calligraphic X?
No. No. Contractions are sort of symmetric. They get rid of, right, if you contract, you end up contracting one Greek letter and one Latin letter. So you lower the number of Greek letters and Latin letters simultaneously. So basically this is because we are in an oriented situation, so you're contracting a tail to a head. Okay? Good. Comments, we can relax the conditions that the number of inputs is equal to the number of outputs, and the definitions perfectly make sense, but we don't do it today because tangles always have the same number of inputs as outputs. And the second comment is that there is a colored version. So instead of talking about tangles or other contraction algebra elements that have only one type of inputs and outputs, I could be talking about contraction algebras in which the inputs and outputs have colors. Which all it says is that in addition to the calligraphic x and x, we'll have two functions, lambda and L, where lambda and L map into some finite set of colors. In our case, it's blue and red. In the example that I've just shown, the colors are blue and red, but more generally, they're just letters. Names of variables. Okay? And the condition, we will put a new condition, and the condition is that we are allowing a contraction. I guess I can't spell the word allowed, sorry about that. But we are allowing a contraction only if you are contracting something to something of the same color. So this is allowed, but this is not allowed. Okay? So this will be a colored contraction algebra. Good. So I claim that we can achieve this heaven for the Alexander polynomial. So I have for the multivariable Alexander polynomial. So I have a contraction algebra whose which when restricted to knots or links, namely to tangles with no inputs and outputs, computes the Alexander polynomial, and yet works in full generality, so you can use it to prove skein relations, for example. So we work over a base ring, and the base ring is polynomials, Laurent polynomials in the square roots. The square roots are lightly used. It's mostly the variables themselves that are used, but occasionally there is a square root somewhere. So anyway, the base ring is Laurent polynomial in variables corresponding to the colors. And we set the Alexander, or A, of calligraphic x and x to be the following thing. It's the set of all W's in the exterior algebra with generators corresponding to the union of the Greek and the Latin letters. So for example, if you're looking at A of psi and eta and x and y, then a typical element will look like eta wedge y plus psi wedge eta plus, wedge y wedge x, maybe with some coefficients. Okay, so wedge product. And then the union operation is wedge product, so basically you multiply two things in the standard way. The renaming operations are you just rename the variables, you change the variables. And the interesting operation is the contraction operation. So suppose you have a W in such an exterior algebra, and the exterior algebra includes the generators x and psi. So you can write any such W as a linear combination of things of the form U W prime, where U contains only the two variables to be contracted, so x and psi and x, and W prime is in the exterior algebra in which these two variables are removed. And then you map, and then the contraction is defined by mapping U to 1 if it is 1, or if it is x times psi, and to 0 if it is psi or x. You see, the exterior algebra in psi and x is four-dimensional. It's generated by 1 psi x and x psi, or x wedge psi. So basically, if I see 1 times omega prime, I map it to omega prime. If I see psi times omega prime or x times omega prime, I map them to 0. And if I see x psi omega prime, I map it to omega prime. Of course, everything is happening in an exterior algebra. So if I see psi x omega prime, that's just the negative of what I wrote. So it goes to the negative of W prime, sorry. So a simple proposition is that what we got is a contraction algebra. The only hard thing to check is to check that contractions commute. And this is essentially trivial, you know, if you pull out psi and x, and if you pull out y and eta, it doesn't matter in which order you pull them out. Okay? So it's easy to check that it's a contraction algebra. I should say that there are various alternative formulations depending on your level of algebraic sophistication. So the contraction of x and psi is also, well, you take W, you multiply it by the exponential of x times psi, and then you apply the interior product operation by x and by psi. If you know about the Berezin integral or about fermionic integration, you could also take W, multiply it by e to the x psi, and integrate d psi dx. The contraction operation also represents composition in exterior algebras. That's a fun one because it's related to my work with Roland on completely other things. But so basically, if you have a homomorphism between two exterior algebras, so the exterior algebra on x and the exterior algebra on y, then that set of, then this homomorphism set is isomorphic to the exterior algebra in variables dual to x, and here it should be y, I'm sorry, the target space is y, not x, so that's a typo, where the dual of x is to be considered as these Greek letters. And then you have the following square. So if you have a homomorphism from one exterior algebra from wedge x to wedge y and another one from wedge y to wedge z, you can compose them and you get a homomorphism from the exterior algebra on x to the exterior algebra on z. But you see, this is isomorphic to the exterior algebra in Greek letters corresponding to X, Latin letters corresponding to Y, another set of Greek letters corresponding to Y, and another set of Latin letters corresponding to Z. This is isomorphic to lambda of X star Z, and you can get rid of all the Y's by contracting them. This is this product over all contractions. And then the claim is that contraction is really composition. And then the final interpretation is that, you see, the dimension of the exterior algebra is 2 to the power the number of generators. So it can be identified with a tensor power of some two-dimensional state space or Hilbert space. Okay? So I could write the exterior algebra, and I have to be very careful about signs when I do that, as some tensor product of tensor powers. And then contraction is simply contraction like in the examples I've shown before where you took powers of a vector space. So these are various alternative formulations. Questions, comments? By the way, I have an hour and a half, right? Not an hour.
Yes, you have an hour and a half. I have a question. So
Yeah.
assume we have a colored knot, for example, by some quantum coloring. Can we extend your contraction algebras to colored knots?
No. So for me, when I say a colored tangle, what I mean is that the strands have colors, but the colors are fixed. So here is a colored tangle. I have 3 strands, each one has a color, but the color runs from the beginning to the end. Okay? Good. Okay. So now I want to construct a morphism of colored contraction algebras, going from the contraction algebra of tangles to the contraction algebra I've just defined, the exterior algebra one. Okay? Maybe A is for Alexander, maybe it's for Archibald because it's a version of Archibald's thesis, I don't know. Okay? So all I need to do is to define this morphism, and by the way, my convention is to use as a name for the morphism, I'm using the target space. So the morphism is also called A, calligraphic A. So I only need to tell you what is the value of A on the generators of T. Okay? So T has 2.5 generators. So I just need to give you 2.5 values. The generators are the positive crossing, the negative crossing, and, well, for easier work later, it's actually better to extend tangles a little bit by inserting a thing called a point. And the only role of a point is just a strand in which the label can change. So basically, a point is just a strand whose beginning is labeled I and whose end is labeled J. That's it. Okay? So, my convention for naming is the following. So, you see, I call a crossing X if it's positive and X bar if it's negative. I list the labels, the Greek or Latin letters that come around this crossing, going counterclockwise starting from the incoming lower strand. So here the incoming lower strand is the one at the bottom right, so I go IJKL, and here it will be IJKL starting from the one on the left. And finally, I need names for the colors of the strands. So the upper strand will be colored T, the lower one is colored S, and then the symbol for this crossing is XIJKST, IJKL S and T, and this one is X bar IJKL S and T, and similarly there is a name for the point. So I need to tell you, yeah?
Excuse me, why do you need an exponent here?
Exponent?
Yes, the row has no exponent, so we have just matrices.
I didn't even speak about this yet. You're running ahead of me. Please, let me speak.
Okay.
Okay? Now I am about to define this Archibald multivariable Alexander invariant. So it maps Xijk, well, it maps the overcrossing to t to the negative 1/2. T is just a variable, so it's t to the negative 1/2 times the exponential in the exterior algebra of the following quadratic expression. So psi L psi I multiplied by the matrix 1, 1 minus t, 0 t, psi j, psi k. And there is a similar definition for the other bits. This is, by the way, a very, I'm writing it as if it's complicated, but exponentials in exponentials in exterior algebras are finite sums. Because at some point variables will repeat and you will get 0. So this is really a short finite sum. It's just 1 plus the quadratic thing itself plus a single extra term which involves all 4 variables. Okay? But, okay, now to answer Vasily, why do I take the exponential? Oh, sorry, even before that, you know, people who know the Burau representation will notice that these are the matrices that appear in the Burau representation. And to answer Vasily, why do I need the exponentials? Well, I'm not doing the Burau representation. I'm doing the multivariable Alexander polynomial for Tangles, and it's a different story. I mean, if I want it to have good contraction operations, I need to go into a bigger space. And you'll see again in a few minutes how it works. Anyway, here's the theorem, which I will not prove, but it's not hard to prove. So if you have a classical link diagram with k components labeled t1 up to tk, you have to keep one of the components open. So really the links that I'm talking about are links like this, where one component remains open. And if MVA is just a name for a variable, for a polynomial. It's the multivariable Alexander polynomial of the closure of D. So if this is D, the closure is when you close it into a link. Then the A invariant of the diagram is this multivariable Alexander polynomial times various silly renormalization factor. So some fixed factor in the exterior algebra. So basically this should be labeled by some Greek letter, this should be labeled by some Latin letter, x in and x out, and you get this factor. Then some fixed polynomial, no big deal. And finally some monomial that depends only on the rotation numbers of the components. So if you have a planar diagram, then in addition to not theoretic properties, it also have rotational properties. So basically, how many times did you turn counterclockwise when you traversed a component of the diagram? So basically this A invariant contains the multivariable Alexander polynomial. You have to read it out with some by using some normalization factors. If rotation number concerns you, then I should say that the whole story would be even more natural if you were talking about rotational virtual tangles, but I don't. But that takes us too far aside, so I will not mention that. So just say, keep in your mind that there is a minor monomial issues with rotation numbers. Okay, I will not prove it, but I will demo it. So you see, I don't believe myself. I know I'm so good at making mistakes. I'm amazingly, incredibly good at making mistakes, believe me. So I don't believe myself unless I implement something and the program runs. So I want to tell you about implementing A. Now, the implementation is available is written in a language called Mathematica. It's available on the web as alpha.nb in the following URL. So actually the talk has a URL and the video of the talk will appear on it later, and it's drawbn.net/mo21, Moscow 2021, and then just add /ap and it will get you to a page where all the programs lie. And so you can look at it later, but all I want to do is to go through it very, very, very quickly, basically to prove to you that I'm serious. Okay? I first implement wedge product. So I first implement a container for elements of an exterior algebra. It's called wedge. So basically wedge of AB is a different name for A wedge B. And then I implement something called the wedge product. So the wedge product is well, again, I will not go through the implementation, but this is the complete definition, the complete implementation. So if you compute the wedge product of the empty wedge product with the single generator A with minus twice B wedge A, and you compute the product of this with wedge, the empty product, minus 3 times B plus 7C wedge D, you punch it into the computer and the computer tell you that the output is whatever is written here. Okay? Next, I implement exponentiation in exterior algebras. So this is basically, you know, what is the exponent of something? The exponent of A, e to the A, is sum of A wedge to the n divided by n factorial. So you just wedge A with itself repeatedly, and each time divide by factorial. So this is done here, 2 lines of code, and here's what you get. So if you look at the wedge exponential of A wedge B plus C wedge D wedge D plus E wedge F, you'll get this thing, and notice that it's a finite expression because exterior algebras are actually finite dimensional. So this terminates, the series terminates at some point. Okay, next, I implement contractions, and this is a bit of a mess, but well, maybe I will not go through it, but again, it's a relatively short thing, and we can check it. So, I mean, if you contract D and C inside the exponential written here, well, you get this answer, and you can check for yourself that this is correct. Next, I implement a container for elements in A. Okay? So an element in A is really a quadrupole. A list of input strands, a list of output strands, a list of input ends, so a list of Greek letters, a list of Latin letters, output strands, a list of colors, So a rule that assigns to each end a color and a payload. So omega is the most important thing. It's the payload. It's an element of an exterior algebra. Okay? So for example, the A invariant of a crossing is defined to be, well, the input strands are L and I, the output strands are J and K, the color rules are written here, and the payload is exactly the formula I wrote before. So the exponential of this Burau thing, and then there is unfortunately some linguistical constructs around it. So, for example, the A invariant of the crossing 1, 2, 3, 4 with a lower strand color U and upper strand color V is, well, the expression written here. Okay, next. So, whoa, what happened? Yeah, okay. So similarly, I need to define the undercrossing and the point. The definitions are written here. Then I need to define a linear structure. So how do you add things? You add them. So you add W1 and W2 by adding their payloads, provided all the other information is identical, provided they live in the same space. Then I have to decide when two things are equal. Two things are equal if all of their parameters are equal. Most importantly, their payloads should be equal. Next, I have a union operation, and I think I'm giving a demo for a two-crossing tangle, but I will not go through it. And then there is the contraction. So the contraction of two A objects, so here, sorry, of an A object, works by you contract the payloads, that's the most important thing, and then you delete the T variable from the inputs, you delete the head from the outputs, and you do various other silly renaming things. So, so here is an example. Contraction of the thing we computed before gives out a certain specific answer. And then I do multiple contractions and automatically and intelligently, and maybe I shouldn't go through it. I'll just tell you that the end result is the program is now done. I'm done discussing the program, and now I can see how it runs. So if you have a tangle, I can compute its A invariant very easily. Namely, I label all the edges 1, 6, 3, 4, 2, 5. I label the components by giving them colors. So this component is colored U and this component is colored V. I punch in the crossings. So the lower crossing is, by my convention, is X. I just go through the labels in order. So 4, 1, 6, 3, and with colors V and U, and the upper crossing is X bar 3, 2, 5, 4. Oh, and the programs were intelligent enough, you didn't see it because I went through it really quickly, so that you need to specify the colors of the strands only once. The moment two strands are contracted, the one in which no color was given assumes the colors, it gets contracted too. Okay, so if you contract two strands and one of them was not yet named, was not yet given a color, then it takes the color of the strand you connect it to. So the A invariant of this particular tangle is this. So the inputs are 1 and 2, the outputs are 5 and 6, right? The inputs are this one and that one, the outputs are this one and that one. The color names are as follows: and the actual payload, the invariant, is an element of an exterior algebra with coefficients in the ring of Laurent polynomial in those variables u and v. So square root of u times square root of v times the empty wedge product, and then all sorts of more complicated things. Okay. But you see, I'm talking about this as if it's an invariant, but is it really an invariant? The point is that the moment I have a program that computes everything for tangles, I can compute it on the left-hand side of the Reidemeister 2 move or on the right-hand side of the Reidemeister 2 move. And if I get the same answer, I have an invariant. So, the left-hand side of the Reidemeister 2 move is this tangle, is this pair of crossings. The right-hand side is just a pair of points. I'm asking the computer to compare the two things, the invariants of the two things, and the computer outputs true. So we are invariant under Reidemeister moves. To be honest, there are two types of Reidemeister moves. There is Reidemeister move in which the two strands are oriented the same way, and a Reidemeister move in which the two strands are oriented in opposite ways, so I need to check the other one as well, and the computer also says true. Similarly, Reidemeister 3, I just punch it in, hit enter, the computer says true. Reidemeister 1 is a bit messier. So there are three versions of Reidemeister 1s. They all check, but they only check because I've inserted factors that are related to the rotation number. So basically I get a tau. So tau is the name of the color if you don't mention a color. If you don't use a color, the color is tau. If you don't specify a color, the color is tau. So, so basically for the two clockwise rotations, you get tau to the negative half, and for the two counterclockwise rotations, you get tau to the 1/2, and hence you need this rotation number correction when you compare with the multivariable Alexander polynomial. Here is a comparison with the multivariable Alexander polynomial. So in fact, this is a tangle whose closure is the Borromean link. I have fully labeled it, and then it actually has 8 crossings. There is also a way of writing the Borromean link with just 6 crossings, but I chose one with 8. Okay? So here are the 8 crossings. 1, 2, 3, 4, 5, 6, 7, 8. I tell the computer to compute the A invariant. Look only at the payload, so look at only the last bit, and factor the result so that it would not look like a big mess, but, well, basically it comes out nicer when you factor it. You get this answer, and this answer, which I call A, compares with the MVA. The MVA I took from some note table, it's equal to this, and basically I enter the formula and the computer says that it's true. Good. Okay, but now I can go and check lots and lots and lots of skein relations, and I'll do it very quickly just to impress you that I can do it, but without deriving anything out of it. So there is a relation called overcrossings commute. Here it is, tested, the computer says true. There is a relation called undercrossings commute. It actually is not satisfied. It's not a skein relation. You test it, the computer prints false. That's good news, because otherwise I could cheat and just write a program that always outputs true. Okay? Next, there is a Conway relation, the very famous Conway relation for the Conway polynomial. If the two strands have the same color, then overcrossing minus undercrossing is some expression times the smoothing. You punch it in, you hit true, and you get a bonus picture of Conway. Then there is a second set of identities by Conways, written here. I'm not going to even read them, but you punch them in, the computer says that they hold, so you know that they're satisfied by the multivariable Alexander polynomial. Then there are virtual versions of those by Jana Archibald. Again, you punch them in, the computer says yes. Then there is a third identity by Conway. The sum of these four tangles is equal, basically the Skene relation written here. This plus this is equal to that plus that. It's also what I started the talk with. Again, you punch it in, the computer says it holds. Then there are virtual versions by Archibald and they hold. Then there is Jun Murakami's fifth axiom, and again you punch it in, it holds, and here's Jun. Then there is two virtual versions and they hold too. Then there are the Jun Murakami third axiom, which is the hardest to state. So basically you look at the following 7 tangles, 2, 1, 1, 2, 1, 2, 2, 1, 2, 2, 1, 1, and so on. And the claim is that they satisfy some linear relation which is written here. So you punch them in, you hit enter, the computer approves. Then there is the Naik-Stanford double delta move. Here is Swati Naik, I think, and Ted Stanford. And the double delta move is well, here is the picture. And the claim is that this is equal to that. You punch it in, you hit enter, but you also, for a change, you ask the computer to tell you how long the computation takes. And you find after 251 seconds, 251 seconds in computer time is eternity. It took a long time. So you find that the Naik-Stanford relation holds. Why did it take so long? It took so long because these are big tangles and we need to do computations in exterior algebras in many variables. The indices here run up to 30. So you get, now exterior algebras are finite dimensional, but if you have many indices, you get 2 to the power the number of indices. So these are big computations, okay? Then there are virtual versions, virtual version 1, second virtual version, both by Jana Archibald, both hold. And we found that we have a heaven for proving Skene relations. You know, I've just proven to you 18 or so Skene relations in no effort at all. I just punch them in and check, okay? So we have a heaven, but there is some problem in heaven. And the problem is this dimension problem. So the dimension of A calligraphic XX, is the dimension of the exterior algebra, is 4 to the power the number of elements of X, or 2 to the sum of the number of indices. This is a big number. And now comes the following key theorem, which in a sense is the content of Halachiva's thesis. And the theorem says that we can drop the dimension a great deal. Okay? So, the theorem actually has nothing to do with knot theory. It's a theorem in algebra, and physicists will tell you that it's a theorem in quantum field theory. It's a theorem about Gaussian fermionic integrals. Okay? But in our language, what it is the following. If we are in the exterior algebra, and if we have a W that looks like a scalar times the exponential of a balanced quadratic, so lambda is a certain sum of zeta over zeta and z running in those two sets of a coefficient times zeta z. So basically this is a quadratic with coefficients which are scalars, and it's a balanced quadratic. It has every term in this quadratic is half Greek, half Latin. Okay? So half input variable, half output variable. And you can check, by the way, that the the invariance of the crossing and of the point, the invariance of the crossings were of this form, right? There was a scalar multiplying, if you go back, an exponential of a quadratic where the coefficients were given by this Bureau matrix. Okay? So the claim is that if you have such a balanced Gaussian and you contract it, the contraction is again a balanced Gaussian. Okay? This is incredibly good news. Why is it incredibly good news? Because it means that we can say that all the work we did in exterior algebras, we could reduce it to the subset, we could restrict our attention to the subset of exponentials of balanced quadratics multiplied by a scalar. Okay? So, in the space of balanced quadratics is tiny. The space of balanced quadratics, the dimension of it is basically the number of terms that could occur here. And this number is just quadratic in the number of ends. So we've gone down from exponential to quadratic, which is great news. There is a little bit of bad news here, and the bad news is the word generically. Mostly you can do it. There are exceptions. We will see the exceptions in a moment. Anyway, let's prove this theorem. So, proof. So, first of all, recall how was the contraction defined. So if you want to contract 1 times w prime or xi times w prime or x times w prime or x psi times w prime, where w prime is independent of x and xi, then, well, you get 1 or 0, you get 1, 0, 0, 1 times w prime, depending on which case you started from. I'm just recalling what contraction. Now, suppose I want to contract an exponential. So I want to contract e to the lambda. So I write lambda in a language that makes this easy. So I write lambda as mu times plus eta times x plus psi times y plus alpha xy. So basically, I factor out the terms with x, with y, and with psi x. So mu is a scalar, sorry, mu is an element of the exterior algebra with the variables x and psi removed. Eta is the same, y is the same. So x and psi are the given variables, so all the other variables, mu, eta, and y, are the elements of the exterior algebra with these variables removed. And alpha, so alpha multiplies psi x. So alpha is a coefficient of something which is already quadratic. So alpha must be a scalar itself. Y is linear, eta is linear, and mu is quadratic. Okay? And then I ponder e to the lambda. What's e to the lambda? So e to the lambda is a big sum that starts far on the left and continues into the infinite right. Actually not infinite, finite, because we are in an exterior algebra, but continues far to the right. But the kth term is 1 over k factorial times, well, basically lambda multiplied by itself k times. Okay? So here is lambda again, k times. Now, I want to look at the contraction of x and xi inside this thing. There are two parts to the answer. One part is if in the contraction, if I get a contribution to the contraction from a term that has no xi, no x, no xi and no x. So basically from the part that is independent of x and xi. Well, but that part can only come from, well, you know, if you use any of these factors, you get one of the forbidden variables. So the only way you can get a contribution from here is if you're looking at the mu from here, the mu from here, the mu from here, and the overall contribution when you sum, well, this is simply, well, here you'll get mu to the k divided by k factorial. If you sum, you'll get e to the mu. So this is the contribution to the contraction from the term proportional to 1. Then I want to look at the contribution to the contraction from the term proportional to x times xi. So I need to get x times xi out of this big product. There are two ways it can happen. Either the x and the xi come from the same factor, namely they come from one of those alpha xi x terms. And then I just have to sum over all possibilities for which factor it could be, and you can check, so they come from one factor, all the other factor must be mu's, and you can check that you get minus alpha times e to the mu from this contribution. And then the last possibility is that the x factor, the x term will come from one factor, and the xi terms will come from another factor. And you can check that this contribution adds up to eta y e to the mu. So the overall result is that the contraction of e to the lambda is the sum of these three terms, which is written here. And now comes something clever. So this is e to the mu times 1 minus alpha plus eta y. Remember, alpha is a scalar, eta and y are linear, so this is again a quadratic. I can pull out a factor of 1 minus alpha, so I get 1 minus alpha times e to the mu times 1 plus eta y divided by 1 minus alpha. Notice that I've used division. So if alpha is equal to 1, oh, this is the fire alarm. Okay, I'll try to ignore it, but
All residents, the monthly fire inspection.
Do you hear that?
Please disregard any alarms. These are only tests. I repeat, they are only tests.
Just a little, just barely here.
Okay, good. They're making an announcement on the public alarm on the PA system that everything is just a test. Okay, I'll try to speak, but it will be problematic. Anyway, if alpha is equal to 1, the trick fails. Right? Because I'll have division by 0, because I divide by 1 minus alpha. So the trick almost always works, but if alpha happens to be 1, we're in trouble. Anyway, this is 1 plus a quadratic. 1 plus a quadratic is actually e to this quadratic. Sorry, it's a quadratic which is of rank 1. It's a single summand, a product of two linears. Because all other, like if you expand e to the q, the next term beyond 1 plus q will already vanish because we are in an exterior algebra. So this is really the e to the eta y times 1 minus, divided by 1 minus alpha. and then I can combine the two exponentials, and I get a scalar times the exponential of a quadratic as asserted. Maybe it's a triviality, but it's a very useful triviality. So what's next? So therefore, like we had this A calculus, this Archibald-Alexander calculus, there is gamma calculus. So in gamma calculus, instead of saving the whole exterior algebra, we just save the scalar term and the quadratic. So, you know, instead of saving the whole the whole element in the exterior algebra, we only save a scalar and a quadratic. So we get a morphism of contraction algebras from tangles into the ring cross, so the ring is for saving omega, cross basically the space of quadratics. This is where lambda lives, and I use a funny name for it. So it's Greek letters tensor product with Latin letters. This should be parenthesized. So it's Greek letters tensor product with Latin letters over the quotient ring of the ring we worked with, the ring of quotients of the ring we started from. Because I need to use division. I need to have division as well. And then, if you want to contract a pair, omega lambda, so if you have omega and lambda and you want to contract them, you write lambda in this form, and the result of the contraction is what we computed in the previous slide. So this is actually only partially defined, because there are some divisions by zero. You can check, or there could be divisions by zero. You can check that if you work on pure tangles, so tangles that have no closed components, and in particular this includes long knots, then there is never a division by zero. So, well, once I say something, since I don't believe myself, I immediately implement it. So here is an implementation. It goes along the same lines. I will not go through it, but you know, I will only mention these are the formulas that I just put in the previous slide. And then, sorry, I went back instead of forward. So here are the values of the crossings. So now there is no need for exponentiation. And then I do some routines for automatic contractions and silly things. And in fact, I've even added a routine for conversions between A calculus and gamma calculus. So if you have an A object, its gamma is obtained by just looking at the coefficients of the quadratic things. And if you have a gamma object and you want to find its corresponding A object, you just exponentiate. And you can check that the conversions are inverses of each other. You can check, so first of all you can check that the conversions are inverses of each other. Then you can check that if you have an element of gamma calculus, you convert it to A, you contract, you convert back to gamma, it's the same as starting from that element and contracting directly in gamma. Everything works. And now we can do computations. So we can compute the same thing as before, namely the Naix-Stanford double delta move. The claim is that the invariant of this tangle is equal to the invariant of this tangle. I punch it in, but now I use gamma instead of A, so gamma for both tangles. And I ask the computer to print the output along with the how long it takes, the timing. And now it went down from 250 seconds to 1.2 seconds. And the answer is that the relation still holds. And the savings came because we switched from the full exterior algebra to the part of it which is merely quadratics. However, suppose I wanted to prove Conway's third identity. I've already proven it using this A calculus. But if I wanted to prove it using gamma calculus, I have no clue. Okay? Gamma calculus is not linear. I mean, proving equalities, to prove the two things are equal, you don't need linearity. To prove something about the sum of two things, you need linearity. I have no idea how to prove this. So proving this has not become any easier. There are other things I still don't understand. So, you know, the situation is a bit unsatisfactory. So the contraction of an exponential makes sense even if, so this makes sense even if, so makes sense even if alpha is equal to 0. If alpha is equal to 0, the result will not be an exponential. But what will it be? So, can I extend this theorem about contraction of exponentials to so that it will work even if alpha is equal, sorry, not alpha is equal to 0, even if alpha is equal to 1. Sorry, can I extend it to the case where alpha is equal to 1? I mean, so I will need a different small subset of this of the exterior algebra. Instead of exponentials, it will be might be something else, but what will it be? I don't know. Second, I don't really understand. So you know, the multivariable Alexander polynomial has also good behavior under strand doubling and strand reversal. So if you have a strand, there is the operation of reversing its direction, and there is the operation of doubling it. Okay, making two copies of the same strand. I don't really understand it in this A language. And I know that classical tangles, within the world of virtual tangles, their A invariants live in an even smaller subspace, but I don't really understand that subspace yet. So these are my, this is my to-do list. Well, here are some references, and I'm 12 minutes early. So,
Okay,
thank you for listening. Any questions, any comments?
Thank you very much, Dror. I have at least 3 questions.
Sure.
Thank you for a great talk.
Sure.
So the first question of mine is about the Jones, Humpline, Kaufman. Are there any clues to get anything similar for them? So can we do anything similar for the Jones Poly, Humpline, TPT, and Kaufman?
So, in a sense, they were given that way from day one. So, sorry, I want to look at, so they, so one of the examples, sorry, I have to scroll back to nearly the beginning, so just give me a second. One of the examples of contraction algebras was using powers of a Hilbert space or of a finite dimensional vector space. And this is essentially how the Jones polynomial is given in quantum algebra. So for the Jones polynomial and the Homfly and the Kaufman polynomial, you had such things from day one. However, there is no taking the logarithm trick over there. So for the other not polynomials, there is an A calculus, but there isn't a gamma calculus. So there isn't a way to cost save, there isn't a way to reduce the computation to polynomial time. Whereas for the Alexander polynomial, you can reduce to polynomial time. Now, my present work with Roland van der Veen, who is waving and smiling over there, does this thing, or well, is a variant of this for a certain reduction of the Color-Jones polynomial, or a certain approximation of the Color-Jones polynomial, but for the whole thing, there is no log reduction. Yes, other questions or comments?
Dear colleagues, please unmute your microphones and write on the chat line. After that, I will have more.
Sorry, what did you say? I didn't get it.
No, I said I still have questions, but I want to ask colleagues, do you have questions or comments? Please unmute your microphones or write on the chat line.
Yeah. Oh, should I respond to the chat? Is it possible to...
Well, sure, you can respond. So I have two questions. So one is easily formulated. What about mutations? Can you say anything about recognizing mutations by using that? Say for one component, of course.
I haven't fully thought it through. I think mutations, so I think this invariant, right? The invariant described here is an extension of the multivariable Alexander polynomial to colored virtual tangles. Okay? I don't think you have mutation invariance for virtual tangles. Mutation invariance is a property of classical tangles. So the question you asked ends up relating to the question I posed at the very end, namely, can you say something stronger if your tangle is actually classical? And the answer is, well, that's part of what I still don't understand.
Yes, and yet another questions while colleagues are still preparing, I hope. The last question of mine is, well, one of my dreams is that tensors or other things which are not planar should contract not to numbers, but to something like pictures. I mean, for example, if we have skein relations, they will not. Yes?
I know what you're talking about. I have nothing to say. And I know your dream because we talked about it before. You know, we dream in different languages. I don't know what to say.
Okay. Colleagues, please unmute your microphones and, or if you wish, write on the chat line, so whatever way you want.
Wait, should I respond to the question on the chat? What about mutations? What about pictures? All of the questions are from you and I've answered them, so yeah.
Yeah. Okay, please ask your questions, dear colleagues.
Excuse me, I have a question. Excuse me, can you hear me?
Yeah, I can hear you.
Oh, thank you. I'm confused. I'm curious about the topological explanation of these constructions because I see only algebra.
Yes. So I'm not sure what does topological explanation means. It depends on your starting point. Okay, but I can tell you. So you know, you're right that there was only algebra here, but it was extremely simple algebra. I mean, if you actually compare it with various topological definitions, it's not harder. Okay, so it's not okay, but still, nevertheless. So typically, the multivariable Alexander polynomial is defined by doing something like, so you have a tangle. Sorry, I mean my tangle will be very, very schematic. Sorry, not a tangle. You have a link. You map it to a matrix by doing something topological, deciphered pairing, I don't know, something. And then you compute the determinant. Maybe you remove a row, remove a column, divide by something, but I mean, in principle, you compute the determinant and you get a polynomial. Now, suppose you have half of a link. So, if you get half of a link, namely a tangle, so a thing that looks like that, okay, then, and you do the exact same procedures that goes into matrices, the matrices that you will get, instead of being square, will be rectangular. Okay? And now you no longer have such a thing determinant if it's a rectangular matrix. Instead, you have a large system of minors. So whenever you choose an equal number of columns as you had rows, you get a determinant. So instead of a single polynomial, you get a system of minors. Those minors are organized by choices of columns. And that at the end amounts to, they correspond to choices of things in the exterior algebra. So basically these minors become the coefficients of expressions in the exterior algebra, and these are the expressions that I've been talking about. So,
thank you.
Okay, so by the way, who am I talking to? You're not on video, so I don't know who am I talking to. No name. It doesn't matter. Fine. Okay. So basically, and in fact, this is the history. So the way Archibald, when she was my student, got into, well, she didn't quite get this. She got a variant which I now modified. I mean, but the way exterior algebras came into the business was exactly this. We were looking at rectangular matrices. We wanted to summarize the information. The summary was an element in an exterior algebra. And at the end, it turns out that describing it all from the beginning in terms of exterior algebras is much easier than remembering the history.
Thank you. So may I say that actually you still construct some Cypher surface for a tangle and consider its infinite cyclic cover space and consider its first homology modular. This is the topological meaning of your polynomial.
I don't want to commit to that, because that's actually not, there are several constructions of matrices. And the matrix we used when Jana and I, when we were thinking about it 10 years ago, was not coming from a ciphered surface and the ciphered pairing, but it was a matrix coming from the Wirtinger presentation. So there may be a ciphered way of getting the same or a similar thing, but that's not what we did.
Okay. may true or may not true. Oh, okay. Oh, thank you.
Okay, thank you very much. Are there any further questions or comments?
Right, yes. So, hi, Joe. I'd like to ask you something, but a couple of things.
Jorge, yeah, yes, yeah.
So the first one, it's just something that I didn't get when you explained it. So, for the gamma calculus, you said that your construction algebra was something like R times and a tensor product of R slash R. So can you repeat that part, please? Because I didn't really get what you meant with that.
Yeah, maybe I was too fancy. So basically oh sorry, it's a bit further back. The contraction algebra, right, so instead of saving this whole thing, right, instead of saving the value of the exponential, I only need to save the omega and lambda. Omega is just a scalar. Omega is just an element of the ring. And lambda is a quadratic, a balanced quadratic. So it's an element of, so what's a quadratic? It's an element of the tensor product of the space generated by the calligraphic x with the space generated by the Latin x, but it's a tensor, the coefficients are in the quotient ring, the ring of quotients of the ring we started from. So if instead of polynomials it will be rational functions. So so it's the tensor product of R divided by R. Okay, so that was so an element of gamma calculus is an element in this Cartesian product. This Cartesian product is not a linear space in any meaningful way. Okay? By chance, you can add elements here. Right? By chance, R is a linear space and the quadratics are linear. Okay? But its linear structure is useless. It has nothing to do, I mean, the contraction operations are non-linear as written here. So yes, it's a linear space, but it's pointless to think of it this way.
Right, yes, but you just simply meant that you wanted to take this lambda, but also allow not only coefficients in R, but rather rational functions, right? Or
yeah,
just in the chat that frac R, right? So the fraction field, something like that.
Yeah. Yeah, I mean, I don't know, is there a standard notation for the ring of fractions of a ring? There must be, but I don't remember what it is. So I wrote R divided by R.
Jesse suggested frac R, so I would also use that, I think. Well, I mean, never mind, it's just like notation.
I mean,
so
if you do frac R, I think you get something else.
With the lash, I would say.
Yeah.
With the slash.
Yeah, okay.
Okay.
Yeah.
So something else is maybe, so for both, well, for the Jana calculus, you also mentioned closed components. So you allowed yourself to take closed components. So should I be surprised about this? Because I am, but maybe I'm not sure if I shouldn't be. It's just because I don't understand this well enough.
I don't have a handle into your psychology, so I can't tell you if you should be surprised or not. Closed components are allowed. Contractions don't. When you contract, you don't know if it will give a closed component or not.
Right. It's just because in general for this setup, sometimes you don't allow yourself to take closed components and you just restrict to open tangles, right?
So everything is defined, for what you're not, so this A calculus, in this A calculus, you are allowed to have closed components. Everything works perfectly for closed components. Okay, if everything is closed, so if all the components are closed, you get 0. You can prove, you get 0. Okay, it's still allowed, it just happens to be 0. Okay, so if you want to get an actual interesting invariant, you have to leave one component open and compute before that last closure. So in fact, when I was computing the invariant of the, sorry, I pressed the wrong thing. When I computed the invariant of the Borromean link, where was it? God, that was early on. So, oh no, now I went too far. So when I computed the invariant of the Borromean link, yeah, sorry, I went to, oh, here. When I computed the invariant of the Borromean link, I, sorry, the closing I did by hand. It's in my handwriting. The actual slide had it not yet closed. So the computation was done for an open tangle, and the theorem in the page before said that the invariant of the open tangle you get by opening one component is essentially equal to the multivariable of the fully closed thing.
Okay, so any further question?
Thank you.
Professor, I had a question about the gamma invariant. What's the main advantage of using the gamma invariant over using the A invariant? Like, what information about a tangle does it encode that the A
Oh, it
invariant-
loses information. It has less information because there are some tangles for which it will not be defined, right? If you need division by 0, you don't know what to do. But it's way faster to compute. So in fact, right, it's way faster because it lives in a much smaller space. So in fact, computing just the Alexander polynomial, not the multivariable, the ordinary Alexander polynomial, meaning all colors are the same, using gamma calculus is the fastest known algorithm to compute Alexander polynomials. Whereas the A calculus is far from its exponential time, it's definitely not the fastest.
I actually have a question, if I may, but it's not directly related to the subject of the talk. So the question is about the following, that we're trying to apply Alexander polynomial, let's say the twisted Alexander polynomials, the study of causality in space-times. And we were wondering, are you aware by any chance of some effective way of computing the twisted Alexander polynomial, say using the chain relations or anything like that? Because the papers that we found, they deal with hyperbolic knots and or links.
Unfortunately,
we would like to have something which is computable and
unfortunately,
preferably with the K modules, but this is not necessary.
Unfortunately, the answer is no. I have nothing to say about twisted Alexander polynomials.
Okay, thank you very much.
Sure.
Okay, please, are there any further questions or comments, remarks?
Yes, a question.
Yes.
Yes, please.
Yeah, so you kept mentioning the A polynomial. I didn't quite understand that. Is it related, sorry, A calculus, is it related to the Fox calculus?
The A invariant, or what?
The A calculus.
The A calculus. So, well, the A calculus is what I talked about. The whole talk was about it, right? This was this calligraphic A. Oops, sorry. I'm not with the right mode. So this was this, this calligraphic A calculus, okay? And is it related to the Fox calculus? The answer is yes, and I sort of implied it in in my answer to like 3 questions ago. So when I spoke about how this whole thing came via a long process from computing from doing determinant-like things to non-square matrices, then these non-square matrices come from Fock's calculus and the Wirting representation. So, you know, if I wanted, you know, you could factor it, you could put another step here in the middle, and this will be pi 1 and Fock's calculus.
Okay, so any more? Okay, so thank you, Dror, again for a wonderful talk. So thanks everyone for coming, for good questions, and hope you will give more talks here. I always enjoy your talks, so thank you very much.
Thank you. Okay, maybe in 2022.
Okay, thank you. Bye.
Okay, I'll turn off my video. By the way, everything is recorded and